Okay, part 3 of my Virtuoso videos follows along chapter 5 in the Brunven book. In this version, we're actually going to go through a VLSI CMOS layout, and we're going to do a very simple inverter. We're talking about making an inverter, and so I want to talk about doing the design for a CMOS inverter, and we can remember that from a schematic perspective, we always have the two transistors. We have an NMOS as a pull down, be down here, and we'll have a PMOS as a pull up, giving us our output here, and we'll connect our input gates together. And if we were to try to turn this into a stick figure, we're going to represent the kind of split between the two gates, and so the PMOS gate and the NMOS gate, and we're going to have a connection for, we're going to end up with a connection for the gate, which we always draw in here as silicon, polysilicon, and in fact that's going to have our input. We're going to have the power and ground. I'm going to make them a little bit bigger. So we have power, we have ground. We're going to have a connection here, and we're going to have a connection there, and then we're going to connect these two together, and that's going to give us our output. To start off, what I really want to do is make a schematic and a symbol version before we jump right into the layout version. So in this part of the video, I want to review what it takes to lay out a simple inverter in the CMOS logic. And we have the basic understanding of the kind of schematic, the stick diagram. What I want to try to do is go from here to what we have to do to lay this thing out. There are a couple of rules that we have to remember, because they're going to drive how we do the actual circuit layout. And the first rule of thumb, of course, is we have to know our lambda. And when we go into Virtuoso, this is going to be used to define the sizes of shapes and the distances between things, and I find it handy to kind of keep a list of what those rules are, and maybe even like what the ideal sizes of everything are going to be. The other thing that we have to remember is, just as a note, the source and drain of any of these things, they all need to be laid out in such a way that their shapes are going to be defined as being inside of an active well and inside of a select for their type, and not covered by poly. And the gate is going to have something very similar. It's also going to be active and select, and in this case poly. So for example, if I were to define an area of just I'm going to draw it out here for just a second, an area that I wanted to be the source and drain of a transistor, and I were to draw the gate right through the center of it, that would mean that this would be separated, that the area, if I were to look at it underneath, the area kind of underneath, you'd have your substrate, you'd have, oops, did I get the color? You'd have an area of doped material, and then on top of that you'd end up with your gate. But the AND property and the AND NOT property is going to mask these areas off. The important thing is none of that's going to happen if we're not in a select, and that would actually be a select would be drawn around this whole region. Not a very good artist. And then this green area would actually be defined as an active area based on the type of transistor we're making. It would be N select or P select. So if we were to try to start off our inverter, let's say that we're going to have the NMOS on this side and the PMOS on this side. So on our side view, and then that would mean NMOS and PMOS. So what we're going to try to do first is pick an area that's going to have our active area, and select area, and in here that is our source and drain for our NMOS transistor, and we'll have a region that's going to be our source and drain for our PMOS transistor. And we're going to draw them initially as a box, and we're going to remember that masking property that Virtuoso has. When we come back later and fill it with the gate, color. When we come back and mask this thing with the gate, that's what's going to separate these two parts. So by simply drawing a box and then putting the poly down, that will create the region of separation between these two and the channel underneath. So on the side view, that's going to look very familiar to kind of the logical diagrams of how we're accustomed to seeing these things. So we have our NMOS down here, source and drain. We're going to have, change color. We're going to have our PMOS, drain and source. And then on a sideways view, we'd construct these things on top of each other. And of course they would actually be lined up differently. So this isn't really a typical side view. This is kind of like cut in half, I guess. Looking down, so yeah, this would be the N side, this would be the P side, but they'd be lined up in a straight line based on the gate. We are also going to have to define the select layer to select the region that is going to be N and P type material. Has a much smaller footprint, and one thing that's important is the gate for the P-type has to line up with the edges of the select layer. We don't want to have any holes in our design. The trick about the PMOS is it needs a much larger select layer. And the reason why it needs such a large select layer is because we have to dope an area around the PMOS to make it an N-type, so that this channel here becomes an N-type. So effectively we're going to have this area in here become an N-well because of this region here. So all underneath here, this is going to become an N-type. One other thing that we've got to make sure that we do is connect these things to power and ground. We're going to have an area up here that is our connection to VDD, and an area down here that's going to be our connection to ground. And then what we're going to need to do is to establish a set of via connections. Let me draw these things in. To go from um, the active layer to the metal 1 layer, and then we're going to have to kind of connect those vias to the same layer so that there's going to be electrical connections from one to the other. And so on a side view, essentially what we're saying is we have metal, we're going to have metal up here, and what I eventually want to be able to do is have a via that goes from there and there and connects to that metal, and from there and there to connect to that metal. And so we're going to have this a similar shape up here. And we've taken care at this point, if you're kind of following along the stick figure, we've taken care of almost everything. The one thing we haven't taken care of is the connection between the two. And we're going to do that with one more set of vias and another metallization, another metal 1 layer that kind of goes and connects these guys. And so that would almost complete everything. We have one more step to complete, and that is we need to complete a via from the poly silicon down here for the gate and another metal connection. And we're not really going to establish anything yet, but eventually we would connect that to the outside of the transistor, and so that the gate has its input. And by the same token, we would have another metal connection. We don't need another via because it's already connected, and that would become our out. Down here and connecting to a via here with a metal layer in between, and we're going to have a metal layer connecting our in and another connection to our out. So those are the things that we're going to try to do in Virtuoso. We're going to try to do each one of these things kind of as I drew it, and we'll see how that works out. Now I am back into Virtuoso on my virtual machine. And before I jump straight into building the inverter, I want to review just for a second where all of these lambda rules come from. And so I've opened up a terminal window, and I'm in the U of U directory, and there's a U of U techlib AMI06. This is the process that we've selected for design and all the constraints and the rules for corresponding to the MOS's process. And if I look at this diva drc.rule file, these are the rules that have been provided to us, and what they're going to define are how the diva tool checks our designs to make sure that they meet the design requirements, the design rules. In other words, DRC is design rule checking, so this is how we're going to check these things. And we can see throughout here that there are going to be a number of messages that are displayed when we violate one of these rules, and we can actually see the code that triggers these things. And so in this language we can see a conditional that says if this is true and this is true and the geometry does not have this or this, then that's a violation of the rule. And so with just a little bit of understanding of kind of what we're talking about, we can kind of see what triggers the rules and then therefore how to avoid them. So for example, if we look down at the CMOS rules, we can see, for instance, where lambda comes into play. So for example, rule CMOS 1.1, the well width must be lambda times 12. So if lambda is 0.3 microns, then lambda must be, or then this well width has to be 3.6 microns. If it's any smaller, then that's a violation of the rules. And the code would the DRC rules would print out a message, CMOS sub M rule 1.1, well width is too small. So that's a really good thing to understand. What I've always done is I've put them into an Excel spreadsheet so that I can put a new lambda value in, and it'll show me all of the actual numbers, so that when I'm designing a transistor, I can look at the number and verify that I've met the requirements. So this is the number of lambdas, and then this is just simply a calculation of this times that, and then that just goes all the way down through all of the different parts. Back into the library manager, and I'm ready to begin my layout for my inverter. We already have the schematic and the symbol that we've done previously. So here what I want to do is I want to make a new cell view. I want to make a new cell view. And of course that window pops up behind. And it already has here that it's set for a layout. And so my view type is going to be layout, and the view name is going to be layout. And so here I'll hit OK, and it brings me into our inverter window. I'm going to make it just a little bit bigger so that I can kind of move around. This is following along with Chapter 5 of the Brinvan book, and so the first thing we're going to do is define our N active region, and then we'll put the select around it and put the parts inside of it. So I'm going to create a rectangle, and I'm going to make sure, oops, sorry, I have the wrong layer. Got to pick the layer first. So I want to have N active selected, and I'm going to hit R for create a rectangle. And we could theoretically specify a size by turning off the enable smart mapping. And from my lambda rules, we know that at a minimum it needs to be 3.6 wide and 3.0 high. And I can just drop that right here onto 0, 0. So that becomes our N active region. Now I can add on to that some contacts, and these are the contacts that are going to go from the source and the drain up to the metal region to carry the current. And so to do that, I'm going to create a via, and the via that I'm going to want to use is the NCC, and that's going to tell me that it's going to go from the N active up to the metal layer, and it'll create whatever select, it expects that everything's already inside of a select region. And since I know that this is going to be my, I know that this is going to be the source of the transistor, then I want to put him on the bottom, and I'm going to have the drain go up offset a little bit, and so those become those contacts. It's really hard to see, and so I'm going to hit Shift F to switch into the other view. And so now I can actually see that there's a metal region, and inside that metal region are these square vias that are going to become the contacts between the inactive region and the metal on top of it. We're almost done with our transistor, except I need to add into that the N select region. So the N select region is going to be another rectangle, and I know that from the lambda rules that it has to overlap by at least 0.3 microns, or sorry, 0.6 microns on either side. And so if I were to add 0.6 and 0.6, that would make this 4.8 microns wide, and the height is going to be 4.2 microns wide. And now I can center this thing. And what I want to do is check it. And so I'm going to drop a ruler into my design. And this measurement ruler lets me set a ruler from here to here, and we're going to check from here to here. And I'm zoomed out too far to actually see any of the distances, but if I zoom in, I can see that we're right on 0.6 there, and we're right on 0.6 there. So I can delete these, and what I'll do now is just I'll save my file, and I'm going to go here to verify, and I'm going to do DRC, and we're going to look into the CIW window, into the CIW window, and there's no errors. So far our NMOS transistor is at least satisfactory. For the time being now, I want to select all of this, and I want to move it. what I found is it becomes a little harder to do the next step if you don't have the origin to go as a guide. Okay, so the next step is to lay out the P-type transistor. We're going to do that by the same process that we did for the NMOS transistor, just a few things change. We're going to do P-active instead of N-active. We're going to do a PCC via instead of an NCC via. We're going to create a longer transistor, so the length is, the width is actually going to be 6 microns wide instead of 3 microns wide. And then we're also going to surround it with a P-select instead of an N-select. So to do that, we're going to have first our P-active layer, and that's going to be a rectangle whose width is 3.6 and height is 6. And we'll center that right here on the origin. And next I can come in and create the vias. And so the PCC is already selected, and before we put this down on the bottom corner because it was going to be connected to ground. This one we're going to put in the top left corner because it's connected to VDD. This one will go down to the NMOS transistor, so we'll offset that to the bottom right corner. The next thing we can do is we can select our P-select region, and that has to have a slightly larger span around it. So it's going to have that same span, that 0.6 micron around it. So we're going to create a rectangle, and this guy is now going to be 4.8, and we're going to add 1.2 to this to be 7.2. And again, I can kind of use the grid here to make it the right size. Just to show what would happen if I got it wrong, I'm going to offset it by the wrong distance. So clearly not centered. And when I save my file and I do a verify DRC, and I take a look down here in the command window, and it says that I have 2 CMOS rule violations, and it says that I have to have at least 0.6 microns between the overlap of the active and the select. So if I look back at my design picture, I can see here it's saying this edge of the rectangle fails to meet the design goals. So now I can just move that. So I can click on move, and looks like I can only move it in one direction. And so that's because I have this orthogonal turned on, and so we'll say we can move it any angle, and I'm going to try to get it down. Oops. And make it centered. And now we can do our verify DRC. Oh, I still have an error. Now it's too much in this direction. Sometimes it's easier, honestly, just to delete the shape and recreate the shape. And this time I'll make sure that I put it at -0.6 and -0.6. And verify DRC. No more errors. Okay. Put them back in the center of my screen. Alright, so that gives us the rough structure of the transistor. I now need to create the N well around it. And the rules for the N well is that it has to be 2.1 microns away from the P select. And so we're going to create our N well, we're going to create our rectangle, and this guy is actually going to end up being 7.8 wide and 10.2 high. And since we know that it has to be 2.1 away, I can use that origin to do -2.1, -2.1. So this area here will be selected to be doped as N. This area here will be used to form the P-type channels. The other thing I can do is I can now create my polysilicon gate, and that's also going to be a rectangle. This time it's going to be just the size of the active, so 7.2, and it's going to be 0.6 wide. Sorry, I got that wrong. 0.6 and 7.2 high, and we're going to just kind of get him right there in the center. So every time I do these changes, I'm just going to do a verify DRC and just double check to make sure I haven't violated a rule. So at this point, the P-type is done, and so we're ready now to join these two transistors. Oh, I didn't put the gate on the NMOS transistor. Okay, well, we'll fix that. So what I'm going to do now is I'm going to move all of this and I'm going to try to get that NMOS centered on the origin again. And it turns out that I don't need to have these quite so far apart. My design rules say that this region here, the end well, needs to be at a minimum of 1.8 microns away from here. So what I can do is I can create that ruler and put a ruler here and get that 1.8 line. And now I can come up here and do a move again, and we'll get him down onto the 1.8 line. And I'll zoom in, make sure I got it right, and really doesn't matter what my eyeballs say. I'll do another DRC check, and so far so good. Now I can look at this and I can tell you that they're not centered, and so that means I need to move this P-type horizontally. So now we can go back to that move tool, and actually if I was really slick about it, what I'll do, let me put the gate in on this. Oops. So here our gate is going to be 4.8 high. Sorry, 4.2 high. And he's going to go right there. And what I can do is put a ruler, and I can measure from here to here, and I see that that's 2.1. And I can do a measurement from here to here, and I see that he's over 2.55. And so what I want to do is select this hole, and we're going to move, and I want to move horizontal, and in the X direction I want to do negative 0.45. And now they're completely lined up, and I can verify that that's 2.1. So now I'm ready to connect the gates to each other, and so I'm going to create a rectangle, and this time I'm going to turn on smart snapping, and I'm going to grab this corner and just drag those two together. So now the gates are connected, and I also need to connect the drains together. Oops. And so what I'll do is I'll select metal 1, and I'll add a I'll go to metal 1, oh darn it, redo. I'll go to create a rectangle on metal 1, and with smart snapping turned on, I can just drag. Let me zoom in a little bit. So now I can connect those two together, and so they're connected, and since I've just made some changes, let me run those DRCs again and verify no errors. So the other thing I need to do is I need to put the contact in for the gate, and so I'll come in here and do a via, and this time instead of doing a PCC, what I want to do is I want to do the M1 poly right into this region here. So that's going to let my gate be connected to a metal layer which we have yet to define. Alright, so far so good. The next thing we need to do is create those metal connections for power and ground. And so let's take a look here at the ground. I'm going to create a rectangle. I'm on metal 1, so that's good. And turn smart snapping off, and the width of this is going to be 7.8, which I have computed before, 2.1 wide, and we're going to want to have it connect so that I am kind of like centered. So if it's 7.8 wide and the center of this would be 3.9, so like right there would be the center. Looking at this x dimension, which is at 2.4, 2.4 minus the 3.9 for the width of this transistor would mean that he would be centered at negative 1.4. I think I've done that math right. Double check that math. 2.4 minus 3.9 would be minus 1.5, sorry. Math in my head, never a good thing. Looks like we can move him. Location for the move. Oh, okay. So, if I wanted to, I could verify that I have it centered. I could measure from here to here is 3.6, and from here to here is 3.6. All right, so that's centered. The other thing I've got is I've got to put the power in, and so that's going to be a rectangle that goes also at 7.8 and also at negative 1.5. But he actually needs to be up a little bit more. I have him too close to the gate. So if I do my design rule check, I should get an error. And I do. So I get metal spacing right there saying he's too close. He needs to be at least 0.9 away from there. So to find the distance, what I can do is put my ruler, okay, and find my 0.9 line. And now I can click on move, and we're going to move him, oh, got the wrong part, him to there. Okay, so now I've got him 0.9 away. I'll verify my DRCs, and it's still saying I have a violation. Metal 1 spacing is still too close. Wonder, it may have to be 0.9 away from there, so sorry about that. Yeah, alright, so now I can move. Okay, and now we can verify DRCs, and there's still an error. Oh, there's an error down here. Oh, look at that. So let's put our we'll move him to there, and we'll do our verify DRC. Okay, and so now there's no errors. All right. So now that we have those, I need to put in taps from the metal layer to the substrate. And this is so that the substrate either has power or ground. But this N-type here really is supposed to have power. So I need to actually have an extension of the N-type that kind of goes around this. It needs to be 0.3 around here. So I'm going to add more of the N-well. So we're going to do a rectangle of N-well. And I'm not going to specify size. Oh, I should have put my rulers in first. So I need 0.3 from here, and I need 0.3 from here, and I need 0.3 from here. So now I can put in my rectangle. And for example, I see that my y is at 17.4 and my x is going to be at negative 1.8. So 17.4, so there to there, and then I can shoot this whole thing down. And that gives me oh no, now I have to move it. So now I can use, or try to use the stretch tool. I want to stretch this line. Sometimes this tool cooperates and sometimes it really does not. Come on. So I'll just delete it. Start over. Create a rectangle. Be a little more careful. Negative 1.8 and 17.4. Negative 1.8. 17.4. And just make sure that we drag down. Okay. Alright. So now I have end well, and what I want to do is I want to create some vias, and I want those vias to be taps, and this is going to be a tap for the end well. So this is basically giving power on the end well, and so let's see, we can kind of get him centered and select, and we're going to have another connector down here on the bottom. And this one's going to be a tap to the substrate, so it's called a subtap, and we'll get him centered. Almost done. The last thing I've got to do now is to connect the power and ground. So we're going to create a rectangle here on the metal 1 layer, and I'm going to turn smart snapping back on, and so transistor has ground, and now we're going to have, oops, and now we're going to create a rectangle and have the transistor get some power. And we're going to verify DRC and hope for the best. Okay, so there are no errors. At this point, the transistor layout is all but complete. The one thing that we haven't done is we haven't assigned any of the pin functions. So as far as the layout tools are concerned, we've drawn a nice picture, but we haven't really drawn a workable design. And actually, if I was really going to be super critical, let's see if we can try the stretch tool. Yeah, there we go. I want to stretch, make a nice rectangle out of it. So the last thing I want to do, in this, at least in this video, is assign the pin names. And so what we're going to do is we're going to assign a pin. And if you remember, now's a good time. Actually, if you don't remember the names of the pins you use, now's a good time to bring up the schematic view that we have, where we said we're going to have in and Y and ground and VDD. The pin names have to be, or are case sensitive, so they have to match, and they have to match exactly. So I'm going to go ahead and create a pin, and that pin is going to be an in, and it is going to be an input line, and it's going to go right there. And now I'm going to create a pin, or I'm going to create a, no, undo. I'm going to create a pin, and it's going to be called Y, and it's going to be an output, and it's going to go right there. And then I'm going to create a, and this has to match, so I'm going to double check because my brain has a terrible time with this, VDD, all lowercase, but it's going to end in an exclamation point. The exclamation point says this is a global symbol, so this is connecting to the global power domain. And as before, it's an input-output. And so now I can come up here and assign our VDD to be this whole region here. And now I'll have my ground, all lowercase with an exclamation point, so it's the global ground. And it's going to be a rectangle, and we're going to have ground occupying the space here. So we're going to do another verify DRC, make sure that we're still okay. So far, so good. Alright, so we have the completed inverter past the DRC checks. The last thing we want to do is make sure that we've actually designed the seam inverter that we wanted to on our schematic. And to do that, we're going to do a layout versus schematic check. The first thing I want to do is I'm going to verify and extract. And this is going to let me extract out the structure that is inferred from this layout. Under set switches, I'm going to keep this extract parasitic caps on. We'll use that for simulation later on. And we'll hit OK, and this will create a new view. I see my extracted view. I can open it and take a look and see exactly what it did. So now that we have that, we can go back to the layout view and go to verify LVS. In the LVS view is going to have, we want to compare the schematic to the extracted. And I'll hit run, and this will run here for just a few seconds. We'll bring up this job here. And it says LVS is completed and the netlist match. If, for example, we had something named wrong, then we'd get some kind of an error. And so now it says that the netlist failed to match. And we can see here, for example, in the output it says that these buttons, there we go. So basically we see here that these match, so Y matched, ground matched, and VDD matched, but this net match didn't match, and so clearly we don't have those two things connected. So LVS will help you detect kind of logical faults in your design.